Hello and welcome to lecture 32 of the course Computational Complexity. So, we have been seeing randomized complexity classes such as RP, co-RP, ZPP, BPP and so on, right? Before that we saw a polynomial hierarchy, right? This is we saw sigma 2, pi 2, sigma 3, pi 3 and so on, which were defined as follows. So just so that you could recollect, I have recall the definitions here. Sigma 2 is a class of all languages L such that X is in L if and only if you can verify it using using two quantifiers such that X is in L if and only if there exists Y such that for all Z the verifier can verify the existence of X using Y and Z. And pi 2 has two quantifiers also, but it appears in the other order. First the for all quantifier followed by the there exists quantifier, right? So, and this is sigma 2 and pi 2. This is the definition that we saw. Later we also saw another definition using Oracle Turing machines. We saw that sigma 2 is equivalent to NP with a SAT oracle and pi 2 is equivalent to co-NP with a SAT oracle, right? We saw that. And one would think that the BPP, the randomized complexity classes, and these are kind of different beasts, right? So you have on one hand you have quantifiers, alternations, oracles and so on. On the other hand we have this randomness, bit strings are generated randomly and that is used to verify. Interestingly, in this class we will show that BPP is actually contained in sigma 2, right? In the previous lecture, I mentioned that it is not known whether BPP is contained in NP. However, it was shown that BPP is, even though we still don't know whether BPP is in NP, now we know that it is in sigma 2. And this was showed by Sipser, Gaxon, Loteman in 1983. What happened is Sipser showed that BPP is contained in the polynomial hierarchy, followed by Gax, who showed that it is in sigma 2, in fact sigma 2 and pi 2. Okay, so in fact we will see that BPP is in sigma 2 as well as pi 2. And further Loteman simplified the proof and made it more easier to present, and in fact that is the version that we will see in today's lecture. So BPP is contained in sigma 2 intersection pi 2, right? That is the proof that we will see today. So first up, again this it may not be difficult to see. If I have not shown this before, I want you to verify this, that BPP is equal to co-BPP. So again, by now it should be clear what I mean by co-BPP. Co-BPP is the class of all languages whose complement is in BPP, right? So basically, if you take it, in other words, BPP is closed under complement, right? If you take a language, take a language in BPP, take its complement, even the complement is in BPP. That's what I am asking to show. And once you have that, so suppose we show BPP is in sigma 2, right? Suppose we show this. Now this implies, okay, if L is in BPP, right, or rather I will remove the if and just write it as implications. L is in BPP, then L complement is also in BPP, right, which is from what we said, BPP is closed under complement, which implies that if BPP is contained in sigma 2, L complement is in sigma 2, which means that if you take a language in sigma 2 and take its complement, that should be in pi 2. So L is in pi 2. So L complement is in sigma 2 implies L is in pi 2. So just by the two facts, BPP is contained in sigma 2 and the fact that BPP is closed under complement, together we get that BPP is contained in pi 2 as well. So what we will show is that BPP is in sigma 2. Inclusion in pi2 is just what I described here. So again, you can stare at what I have written in the top right part and try to follow, right? Otherwise, you could ask questions, right? Okay. Now, let us first see what is the high level idea of showing BPPs in sigma 2, right? First up, we saw how we could boost the probability of success in BPP. We could do the same thing, and so in fact what we saw in the previous lecture was that if we had a machine that accepts with probability half plus 1 by polynomial in x for x in the language, and accepts with probability at most half minus 1 by polynomial x for x not in the language, then you can boost it to get, if x is in L, probability of acceptance is at least 2/3, and x is not in L, probability of acceptance is at most 1/3. Okay, so we could get to 2/3, 1/3, right? So now we could pretty much do the same proof or same idea, but maybe the parameters need to be tweaked and get the following characterization. If x is in the language, right, then we could basically, by repeating or boosting the 2/3, 1/3 machine, we could boost up the probability of acceptance for x is in L to 1 minus 1 by 2 power n. Okay, and when x is not in L, the probability of acceptance is at most 1 divided by 2 power n. What is n here? N, by n I denote the length of the input. Okay, so n here is the size of x, or which is the length of the input. Again, I have written here also, n is the length of the input. And again, just as a reminder, what is the random, what is this probability taken over? Probability is taken over all the random choices. Okay, so the probability, again, once again, probability is not over the input. For any input x, even after you fix the input, the probability can be taken over the random choices, right? And let us say, so for a fixed length input, the random input is also fixed. If the input x is fixed, if the input x is of length n, then the length of the random bits are also fixed. Let's say the random bits are of length m, where m is some polynomial in n, where n is the length of the input x. Okay, so if x is the input and r is the random bit string, so x is of length n and r is of length m, then we denote by mxr, we denote the randomized Turing machine, which takes x as input and r as the random bits, right? So m performs in perfectly or completely deterministic manner, but then all the randomness comes from the fact that r is random. The random bit string is random, right? So once r is fixed, everything is deterministic, right? It's like saying in randomized quicksort, once I tell you what random numbers are going to appear, then you know which pivots are going to be chosen. Everything is deterministic from there on. Okay, so the point here is that when x is in L, you can boost the probability of acceptance to 1 minus 1 by 2 power n. Again, n is the length of the input, and when x is not in L, we can reduce the probability of acceptance to 1 divided by 2 power n, and this can be done by the same boosting argument, just by tweaking some parameters. Okay, so now let us see a different perspective of how this randomized algorithms work. Again, this perspective also may be useful in understanding randomized algorithms separately, but this perspective is particularly helpful for this proof. Okay, so given a string x, right, I spoke about the probability of acceptance over a random set of random bits. So let r, so I said r, the random bit string is going to have m length m, right? So which means it's going to be, there are 2 power m possible choices of r, right? So assuming all of them are equally likely, right? When I say the probability of acceptance is half. This means that, or when I say probability of acceptance is 80%, let's say, this means that out of this 2 power m possible random bit strings, 80% leads to acceptance and 20% leads to reject, right? Similarly, if I say the probability of acceptance is only 10%, this means out of this 2 power m random strings, on the input x, once we fix the input x, out of this 2 power m random strings, 10% leads to accept and 90% leads to reject, right? So now let us call for a fixed x in 0, 1 power n, let us call Sx. What is Sx? Sx is a set of random strings for which x is accepted. Okay, so more formally I will write here, Sx is a set of all r. So here the machine is fixed, x is fixed, okay, is a set of all r such that m x r leads to accept. So if x is in the language, Sx will be bigger. If x is not in the language, Sx will be smaller, right? That's what we want. Okay, now we have done this boosting, right? Again, this boosting, when x is in the language, the probability of acceptance is 1 minus 1 by divided by 2 power n, 1 minus 1 divided by 2 power n. That means out of the 2 power m possible strings, 2 power m possible random strings, 1 minus 1 divided by 2 power n fraction, or this many, right, this many random strings lead to acceptance. So Sx is of size at least 1 minus 1 divided by 2 power n whole multiplied by 2 power n when x is in the language. When x is not in the language, Sx is of size at most 1 by 2 power n fraction, which is 2 power m divided by 2 power n. So let us try to see this pictorially, okay, which is what I have drawn below. When x is in the language, let this box denote the universe of all the strings of length to m, right? So there are 2 power m such strings. So a huge majority of these strings lead to acceptance when x is in L. So I will call this Sx, and I have drawn pictorially. So Sx, you can see, covers almost the entire rectangle. When x is not in L, you can see in the right hand side, Sx is much smaller. It is a much smaller part. Far from covering it, it's covering only a small portion. It's only reaching a small portion. Okay, so with this pictorial idea firmly in mind, I can explain the high level proof. Okay, so this is one of these proofs that has a very clean, interesting visualization at the high level. Of course, you can go to details, delta, epsilon calculations can be done for all the proofs, but this proof has a very clean visualization of what is happening at the high level. And once this, if you understand this, the rest is something that you could naturally work out on your own, right? So when x is in the language, Sx is large, right? As we see in the left hand side, right? Okay, so I'll just make some space so that I can write this. So when x is in the language, Sx is large, right? So what happens when Sx is large is, sorry again, S subscript x, right? So now consider the same thing, the same image here. Same image here, or similar image here. Suppose this is Sx. Now consider, let us move around Sx slightly. Okay, so now let me consider slight shifting of it. Maybe I will shift it slightly. Maybe I will denote it with a green color. Something like this, right? So now it is covering some top part. Now let us say I move it to the bottom some slightly, so maybe something like this, right? And you can see when I am shifting this, it is covering some regions of the original red rectangle that were not covered by SX, right? So the blue part covers some part, green part covered some other part that was missed, etc. So if we move around SX, we can possibly cover the entire universe of the M length strings by this thing. So as it is, you can possibly see that by 5 or 6 movements, 5 or 6 shifts, you may end up covering the entire thing, right? However, when Sx is small, right, Sx is so small, now even if I have multiple copies of Sx, right, so this is Sx, now even when I have multiple copies of Sx, this is not going to cover the thing. So in the case of, in the left hand side, we had even with Sx is so huge, it covers so much of the area that even by shifting around, you may end up covering, by shifting around 2-3 times or 4-5 times, you may end up covering the entire thing. Let's say maybe 10 times you cover the entire thing. But here 10 times, even if they are all disjoint, even then they are not covering in the right hand side, right? And if there is an overlap between some of them, then it covers even less, right? So even though there are 4-5 copies of Sx, but then they are all overlapping, so they cover even less. So the proof idea is this: if Sx is large, then we could shift the Sx around, and all the strings in the universe can be covered, as you can see, using some small number of shifts. However, when Sx is small, right, if you move it around and shift, it is and if you limit the number of doing this operation, moving and shifting, it is not going to be able to cover all the set of strings. No matter, like, if let's say if you limit to 10 movements and shifts, it is not going to cover this entire area. This is because the area is so big, so more big than even 10 times the area of Sx. So even if you spread it all out, even if you could do that, it is not going to help, right? So that is the main idea of the proof, and that is going to lead us to a sigma 2 characterization. Again, the goal, remember, is to show that BPP is in sigma 2. So that now let us try to see what I mean by shifting the Sx. What do I mean by shifting a set? Okay, so consider a set Sx, okay, or so consider a set S, okay, this could be anything. S is a subset of 0, 1 power m, meaning set of all m length strings. It is a subset of m length strings. And consider a specific m length string called u. Now, S plus u, by S plus u, I denote you adding u to all the strings in S. So maybe a very simple example in the right side. If let's say S is 0, 0, 0, 0, 1, 1 and 1, 0, 0, and let's say u is 1, 1, 0, then S plus u is nothing but you add 1, 1, 0 to all the strings. So you add 1, 1, 0 to 0, 0, 0, you get 1, 1, 0. You add 1, 1, 0 to 0, 1, 1. So notice that this addition is bitwise mod 2, or rather bitwise XOR. There is no carry or anything. So 1 plus 0 is 1, 1 plus 1 is 0, 0 plus 1 is 1. And 1, 1, 0 and 1, 0, 0, it's going to be 0, 1, 0. It is bitwise XOR or bitwise mod 2 addition, right? So this is the operation that I refer to by shifting around. Okay. So this is the shifting operation, and we will choose a number k, again this will appear later, to be m divided by n plus 1, or with a ceiling. Okay. M divided by n may not be an integer. So by this, what is assured is that n times k will always be bigger than m, Okay, so this is what we want. N times k to be bigger than m is what we want. This is the smallest such k. We want k to be an integer such that n times k is bigger than m, right? And the smallest such integer is what we choose. Okay, so I hope the high level idea is clear. The fact is that when x is in the language, we can move around Sx some number of times, let's say 10 times, and cover the entire universe. When x is not in the language, no matter how we move it around, 10 times is not going to be enough to cover the entire universe. And the k here is going to be our 10. Okay, so or k is going to be the fixed number of shifts and repeats that we are allowed. Okay, and this will be used to derive a sigma 2 characterization. Let's first show the second part, that when x is not in the language, no matter what shifts we select, k shifts are not going to be enough, and that is just going to be by counting the area of k shifts. Okay, the first claim, so I am writing it as two claims. For any set S, okay, so any set S with the size of S being less than 2 power m minus n, right? So notice that this is what we said here. When x is not in L, size of Sx is at most 2 power m divided by 2 power n, right? This is what we have in the red box here. When x is not in L, it is this is what I am referring to. When S here in the claim 1, when S is such a set S, right? So which is satisfied by Sx when x is not in L. Take any k vectors u1 to uk. Okay, take any k vectors. So S plus u1, S plus u2, all of these contribute to different shifts, right? All of these are different shifts of S, different shifts of S. Now take the union of all these shifts, right? S plus u1 union S of S plus u2, etc. up to S plus uk. This will not be the entire universe. This is what it says. This is what I said in pictorially in a notation form. The shifts are not going to cover the universe. Something is going to be missed, and this is going to be proved by merely a counting argument, right? So in the right hand side, the size is 2 power m, right? 0 1 whole power m, and the left hand side it's a union. So as we know, the union of k sets, the maximum size is obtained when the union is all disjoint. There could be intersections between them, but then the size of the union only comes down. The size is maximized when the sets are disjoint. So let's take the maximum possible. So what is the size of the left hand side? The maximum possible is k times the size of u plus I. So k times the, maybe just write one more line here. This is at most k times size of S plus u plus I, S plus u plus I, but then S plus ui, but then S plus ui is just S shifted by something. So size of S plus ui is the same as size of S, right? So that is why we have k times the size of S. And what is the size of S? We know that size of S is 2 power m divided by 2 power n at most, and we know that k is such that nk nk greater than m. So k is such that m by n plus k is equal to m by n plus 1. So that is not going to be enough to make up this, right? So k times 2 power m divided by 2 power n will be strictly less than 2 power m, because k is m divided by n, and then you have divided by 2 power n, so that's not going to be enough. Okay, so even when n is large enough, even when n is large enough, when n is large enough, just by counting argument, we show that by shifting S by S into k copies, it is not going to cover the entire universe, because the size is, even in the disjoint case, it's not going to be able to cover. Okay, that's the first point. The second claim is to show that when Sx is large, meaning Sx is of the size 1 minus 1 divided by 2 power n multiplied by 2 power m, there is a way to shift Sx k times and cover the entire universe. That is claim 2. For every set S, again this is just any set S with this size requirement, 1 minus 2, 1 by 2 power n multiplied by 2 power m, there are k ui's or k shifts that will lead to the entire universe being covered with these k shifts. And what we will do in order to show this is to show that if we choose ui's randomly, this will come true. Okay, we'll show that it is possible even for randomly chosen ui's. So this is a technique called probabilistic technique. Suppose, so in simple terms, if you roll a die, the probability of you getting a 1 is 1 over 6. So the probability of getting a 1 is non-zero, which means there is some outcome that leads to you getting a 1. Whereas the probability of you getting a 10 in a single die is 0. That is because there is no possibility, right? So what we will show here is for randomly chosen u1 to uk, the probability of this happening is greater than 0. So if the probability of this happening is greater than 0, that means there is some set of possibilities that lead to it getting a non-zero probability, which means there exists some u1 to uk for which this shifts cover the entire universe, and that is enough for us. We don't need to know what they are, all we need to know is the existence of these u1 to uk. So what we will show is, if u1 to uk is randomly chosen, the probability of shifts covering this universe is strictly greater than 0. This is what we will show. Okay. For u1 to uk randomly chosen, the probability of the shifts covering u1 to uk is strictly greater than 0, some non-zero quantity. Because if it has to be even, let's say 0.01, that means there is some minute set of possibility, some u1 uk that occur with this probability that is giving us this non-zero value, right? So that is all we need. We need existence of some u1 to uk. So arguing that something happens because the probability of that happening is greater than 0 is called the probabilistic method. Again, this is a very powerful technique that is often used in many proofs in randomized algorithms and also combinatorics, and this is our first instance of using it in this course, right? So the probability that this is non-zero or strictly greater than 0 implies that there implies the existence of u1 to uk which give us the shifts that cover the entire universe. So provided S is big enough, we know the existence of these u1 to uk. So now let us compute the probability. So the rest of the proof is just going to be estimating this probability and shows that this works. Okay, so consider a string s, small s, in an m bit long string, and let bs be the event that s is not covered by this union of these shifts. Bs is the event that s is not covered by the union of these shifts, and we will show that so we need to show that the union covers everything with probability greater than 0. Instead, we will show the negation, the complement event has strictly less than 1 probability. What is the complement event? The complement event is there is some s that is not covered, right? So S is not, so the union of all any S being not covered, we show that that event is happens with probability strictly less than 1. So in fact, again, this is also possibly going to be an overestimation, because it's a union, and we will just show that even this. So here again we will use the sum of the probabilities. So in fact, what we will show is that the probability of Bs itself, that means probability of S being covered, S being not covered itself, is strictly less than 1 by 2 power m. So the probability of there existing, or the probability of there existing any S that is not covered, is going to be strictly less than 1. Right. So the probability of there exists one S is the probability of the union, and the probability of the union is at most m times, right. So the probability of the union of all S Bs is at most 2 power m times the probability of any Bs, and this we know is strictly less than 1 by 2 power m. So it is 2 power m multiplied by 1 by 2 power m, which is equal to 1. So it is strictly less than 1. So now all that we need to show is that for a fixed S, the probability that S is not going to be in this shifted union is at most 1 by 2 power m. And this will be shown, this probability of Bs is strictly less than 1 by 2 power m will be shown for any m. Okay. So S is fixed, right. So now we will further try to understand Bs. Bs is the probability that S is not covered. So let Bs superscript I, okay, be the event that small s is not in the shift, the ith shift. Small s is not in S plus ui. So small s is not in S plus ui. That is the same as saying small s plus ui is not in capital S, because it is bitwise XOR. So if you add ui to the smallest, then that is the same as, or if you add ui on both sides of the first line, you get that smallest plus ui should not be in capital S, right. So Bs superscript I is the event that smallest plus ui is not in capital S, which also means that smallest is not covered in the ith shift. Okay. So what is Bs? Bs is the event that S is not covered by any shift, meaning it should not be covered by the first shift, second shift, so on up to kth shifts. So it is the probability that, or it is the event that S is not covered in any shift. So it is the intersection of all the Bs superscript I. Right. So so in fact we will estimate Bs superscript I, the probability of Bs superscript I. What is the probability of Bs superscript I, which is the same as asking what is the probability of S plus ui not being in S, right. So in fact, once you shift, so ui is a randomly chosen string, right, and S plus ui is also a random element, right, because ui is random. So wherever you started from, you move somewhere randomly. So now this is also a random place, right. So what is the probability that S plus ui is not in S? We know that S is of size 1, at least 1 minus 2 power minus n multiplied by 2 power m, which means the probability of it not being there in S is less than or equal to 2 power minus 1 by 2 power n, right. So this is because probability of some random element being in S is at least 1 minus 1 by 2 power n. So probability that some random element is not in S is at most 1 by 2 power n. So that means probability of BSI is at most 1 by 2 power n. And this is independent of I, because each I is virtually the same, because every I every shift is a randomly chosen ui. So probability, and each of them is independent. So the probability of the intersection, the probability of Bs, which is the intersection of all the Bs superscript I, is nothing but the product, right? Because the intersection is over independent probabilities. So it is just the product. So it is 2 power minus n whole power k. And we know that k was chosen to be such that nk is greater than m, right? So nk greater than m, so minus nk is less than minus m, right? So we have strictly less than minus m, so we have the probability of Bs being at strictly less than 2 power minus m, and that is all we needed, because then the probability of the union is strictly less than 1, which means that there is some shift, or there is some shift that covers all the strings S in capital S, and that is what we needed, right? So just to recap the proof, we needed to show that there are enough shifts such that we need to show the k is enough such that all the strings are covered, and we show that by showing a random set of k shifts, and the probability that the random k shifts do not cover everything is strictly less than 1, and that implies that the probability that the random shifts cover everything is strictly greater than 0, right? And that is enough to imply the existence of existence of u1 to uk, which are shifts that such that s plus u1, s plus u2, etc., s plus uk cover the entire universe. So what we have is that claim 1 and 2. So first let us see what claim 2 says. If x is in the language, sx is big enough to satisfy the requirement of claim 2, right? And that implies the existence of u1 to uk, right? Such that for all the strings S is covered in the shifts. So instead of S, let me use the letter R, right? It's just a letter change. So for all the R's, R is covered in some shift, right? The union covers everything. So any string R, any m length string R is in the union. This means that, what does this mean? This means that Sx is a set of strings where x is accepted, right? Remember how Sx was defined initially. This is a set of random strings where x is accepted. So if R is in Sx plus ui, this means R plus ui is in Sx, meaning the randomized Turing machine M accepts x when guided by R plus ui. So because R plus ui is in Sx. So if you consider R plus u1, R plus u2, R plus u3, etc., for some I, R plus ui will lead x to be accepted. If x is not in L, okay, so maybe I'll just explain this in the same statement in the. So now you may already be seeing how we are coming to the sigma 2 representation. So same thing, let me try to represent. X is in L, then there exists u1, u2 up to uk, which are the shifts, such that for all R in 0, 1 power m, either m accepts x and R plus u1, or m accepts x and R plus u2, or m accepts x and R plus u3, and so on. One of these k things lead to acceptance. That's the same thing as saying the OR of these k events is true, right? The OR of these k events. So now you can see why it is a sigma 2 representation, because M is a deterministic verifier, right? Deterministic machine. Once R is fixed, M is also M just performs in a deterministic manner, and the union of k such M's, you can run k M's one by one serially or parallelly, it is still polynomial time. So the OR operation over k m's is also polynomial time, and you have outside you have there exists followed by for all, so existential and universal quantifiers as sigma 2 would insist, right. So that is one direction. Now let us also convince ourselves of the other direction just to show. So now we of this if and only if, now we have shown this direction. When x is not in L also we need to show, which is the other direction, right. Suppose x is not in L, then Sx is of size 2 power m divided by 2 power n, right, this, or at most this. By claim 1, whatever u1, u2, uk you try, right, this is what claim 1 said. Any set of k vectors, the shift is not going to cover everything. So whatever u1, u2, uk you try, there will, so it is not going to cover everything means whatever u1, u2, uk you try, there is going to be some r that is not covered. So there is, for all u1 to uk there is an r such that r is not in the shifts. So which is what we wanted to show, which is the negation of this. So now with both of this, claim 1 and claim 2 together, we have shown that x is in L if and only if there exists u1 to uk such that for all r this has to be true. The or of m x plus r, x comma r plus ui has to be true. And this is a sigma 2 machine, right. This is a sigma 2 machine. So we have shown that L has a sigma 2 characterization, which is what we set out to do, right. Just to summarize, so sigma 2 has this characterization. Just to summarize, we want to show BPPs in sigma 2 intersection pi 2, but then we first showed that it is enough to show that BPP is in sigma 2 because BPP is closed under complement, right. So we took an arbitrary language in sigma 2, arbitrary language in BPP, and then we boosted it to such an extent that the set of strings that lead to, set of random strings that lead x to an acceptance covers almost the entire universe, right? 1 minus 1 divided by 2 power n fraction. And if x is not in L, the set of strings that lead x to an acceptance is a very, very small portion of the universe. And now the idea is that if x is in the language, there are k shifts that you can do that covers the entire universe if x is in the language. But if x is not in the language, no matter what k shifts you do, it is not going to cover everything, right. And claim 1 used a bit of probability. Again, you can go through the details. Sorry, claim 2 used a bit of probability. You can go through the details. Claim 1 was merely by counting the size of Sx, and no matter how you place the Sx, it's not going to be enough because the size itself is not going to be enough. And with that we get the sigma 2 characterization for L, which is what we wanted to show. So now we have shown that BPP is in sigma 2 and pi 2. And yeah, with that we have seen a bunch of randomized algorithms starting from RP, co-RP, ZPP, BPP and so on. So now we will after this we will move to another topic in the next lecture, but we will keep coming back to randomized classes because we will keep seeing, so just like we saw how BPP relates to sigma 2, we will keep seeing how randomized classes relate to other complexity classes, which is the whole point of this course, to see how complexity classes relate with each other.